Hi from Democritus. Here we're going to talk about light. We're going to talk about the characteristics, we're going to talk about the secrets of light. Light is all around us. The main source of light on Earth is of course the sun. But there's lots of other ways of producing light, and we can have LED lamps, we can have neon lamps, we can have all type of filament lamps, etc. We can even have lasers. But what are the characteristics, what are the secrets of light? In this video, this is what we're going to see. We're going to see a number of secrets that most people do not know. Light, or more correctly, electromagnetic radiation, is not just one single entity, but it's actually a huge spectrum of different radiations, different types of radiation, that they differ in wavelength and in energy. Starting from one side, where the energy is very high, we have gamma rays. Gamma rays, which is radioactivity, they are such a high energy that actually very dangerous for life. Next to it is X-rays. X-rays also have high energy. They are able to penetrate human, and we can see our bones inside and everything. Both of those are actually ionizing the radiation. Next to it, we have the ultraviolet, ultraviolet C and ultraviolet B and A. C is still dangerous because it's got high energy. We're going to talk a lot about UV later on. And then we have a very narrow portion, which is the visible part of the spectrum. A very tiny, very small portion. That's where our eyes are sensitive to. The rest we cannot see. And on the other side, we have the infrared, also invisible. Infrared comes from hot bodies, and infrared also we're going to be talking about later on. After that is microwaves that are used to heat up water and heat up other materials. And after that is radio waves, where we have communications, we have radios, we have television, we have Wi-Fi, communications with satellites, etc. And beyond that, we have the long radio waves. The spectrum is an amazing characteristic. It's an incredibly wide spectrum. The difference between the long waves and the gamma rays, the difference in wavelength is 10,000 trillion times. 10 quadrillion times. It's the largest, the most wide spectrum in physics. And all of those wavelengths, they're all part of the electromagnetic spectrum. Light at all the wavelengths is pure energy, and is produced whenever there is a release of energy from a mechanical, chemical, and nuclear, electrical system. Now, on the sun itself radiates in all wavelengths, and radiates because of fusion of hydrogen nuclei to produce helium, and there's a huge amount of excess energy. The same way with the thermonuclear explosions, thermonuclear bombs work the same way. They produce a huge amount of energy. Now, the opposite of fusion is fission, which means the splitting of nuclei to produce new atoms. Now, the new nuclei. Now, the splitting, they also release a huge amount of energy, and we have the atomic bombs. But of course, at the same time, with the same method, we can produce electrical energy in nuclear power stations. Now, gamma rays can also be produced in a natural way during the radioactive decay of materials like plutonium, uranium, radium, and other materials, radioactive materials. Now, all the other in other wavelengths, like the X-rays are produced by bombarding a material with high energy electrons, and everything is produced artificially. So we have the infrared or ultraviolet and visible light is produced by giving energy, supplying energy with electrons, with electricity. Microwaves and radio waves are produced by oscillations of atoms. We oscillate the atoms also by giving them electrical energy. And finally, we mustn't forget that hot bodies, all hot bodies, radiate their heat energy in the form of infrared waves. Light throughout the electromagnetic spectrum is a quantum phenomenon. Quantum means that it has a dual nature. We talk about electromagnetic waves, but we also talk about that light photons. Photons are the quanta, are the little packages of energy. And we have high energy gamma rays from one side and low energy radio waves on the other, or radio photons on the other side. But it's not just light that is quantized, but all methods, all ways in nature to produce light, they're also based on quantum mechanics. For example, in the sun and all the other stars, fusion meaning that of hydrogen nuclei to produce helium and produce a huge amount of energy and light, this becomes possible because of a quantum mechanical phenomenon called tunneling. But also in everyday production of light, in all types of filament heated lamps, the filament becomes very red hot and white hot because of a quantum mechanical phenomenon where the electrons go to an excited state, and as they fall down to a ground state, they emit light. That's a quantum mechanical phenomenon, pure and simple. The same, approximately similar type of quantum mechanical phenomenon we have the LED lamps, in neon lamps, and everywhere. Even the toaster, the hot toaster, the filament there that becomes hot and heats up our bread, that's a quantum mechanical phenomenon. But fire, even the light of a candle, that's a quantum mechanical phenomenon. As we said before, the visible part of the spectrum is tiny. It's only between 400 and 700 nanometers. It's an absolutely infinitesimal part of the whole spectrum. It's a huge spectrum. And this is the only part that our eyes and most of the animal eyes, they are sensitive to, and plants as well, of course. And yet, scientifically, we've been able to produce equipment and sensors that we're able to see, we're able to get information, do observations of all the parts of the spectrum. For example, we use Geiger counters for gamma rays, we have Röntgen counters, radio machinery for X-rays, we have sensors for UV, infrared, we have antennas and various radio telescopes for the radio waves, etc., etc. Because each one of those parts of the spectrum gives us different information. And in astronomy, this is terribly important. So as you see in the video, if we look at the Crab Nebula, the Crab Nebula gives us, we can photograph it in different wavelengths, and each wavelength gives us a different information, different part of the spectrum. And if we combine it all together, then we have all that information all in one picture. If you look around you, you'll find that nearly everything has some color. There's natural colors like these leaves, there's green leaves, there's artificial colors like this red cup, this blue cartoon. But exactly what is color? Color is nothing else than a construct of our brain that allows it to distinguish between different wavelengths. So for example, at 550 nanometers wavelength, we see things as green. At 650, we see them as red, and at 450 nanometers, we see them as blue. And that's all it is. It's a way that the brain constructs and translates wavelengths. Some people, of course, can see the same wavelength, 650, but instead of seeing it as red, they might see it differently. They might see it as green. That's achromatopsia. Now, what is white? White is nothing else than a combination of all the main colors. So if I switch on this cool light, the cool LED light, we can see that this is a spectrometer, and the spectrometer shows us that it consists of blue, green, red with a bit of yellow, and the warm white, the difference is that it's mainly red with a lot less blue and green. The neon light is made up also of the same combination of colors. We have orange, red, and we have green, and we have blue, and that again, our brain translates it as being white. That's all it is. All the colors, all the wavelengths that hit the surface of the white paper, they are emitted back, and we see it as white. But what happens with black? What is black? Black is nothing else than an absorption of all the colors that are hitting on the surface. So if this was a white LED, and if we illuminate a black cloth, the black cloth absorbs everything, appears to be black. And all this, so this is what colors are all about, and white light. But what about monochromatic light? We have three lasers here. Monochromatic light, for the first monochromatic light is this one here, it's 530 nanometers, it's green. So if I illuminate now these three items, the leaves appear green, darker green, but the other two items appear to be black. If I illuminate now with a red light, there is a 650 nanometers red laser, and if I illuminate now those two, the red cup appears red, but the other two appear to be black. And finally, and if we illuminate with a blue light, a blue laser light at 405 nanometers, and we illuminate those three, the blue cartoon appears blue, but the other two appear black. And so the reason is, of course, because there's nothing for them to reflect. There's no other wavelengths to reflect, only the color of the wavelength that they're colored. And this is the reason, the way that we understand colors. It's purely a construct of our brains. Even though the solar radiation that reaches the surface of the Earth contains all the wavelengths of the visible part of the spectrum, from 400 to 700 nanometers, and yet plants do not only radiate, show green light, green color. And the reason is that the green color is useless for plants. It is not, you cannot be used for any of the chemical reactions that take place inside the plant. In the full spectrum, we know the full spectrum contains all this is a type of full spectrum, it's not the one, the solar. It has blue, green, yellow, red, and everything. But in fact, the plants need only blue and red. And if I have a light over here, which contains only blue and red, you can see a large amount of blue and a small amount of red. And if I shine this on the plant, you can see that the blue and the red are completely absorbed, because suddenly the plant appears black. So everything is absorbed, and there's no green, the green color to be able to show the color of the plant. And this is how modern hothouses work. They only have this type of radiations, only blue and red radiation for developing the plants. And the reason is, of course, quantum mechanical. That the green color does not have the right energy to give a bump to the electrons to become excited, and so it is radiated away. It is not absorbed. But the blue and the red have just the right amount to bump the electrons, different electrons, at the different excited levels, and then as they come down, they radiate away, if there was something, but they absorb all the energy they have. Light from the sun and other stars is produced by fusion reactions. Fusion of hydrogen nuclei to produce helium nuclei. And these fusion reactions, they liberate a huge amount of energy. That's what thermonuclear bombs are all about, thermonuclear explosions. That energy is emitted by the sun, most of it, in the form of light. Light of all wavelengths, all the way from gamma rays, X-rays, UV, visible, infrared, microwaves, radio waves. The whole spectrum is emitted by the sun. And the high energy waves, that's the gamma rays and X-rays, are called ionized radiation. They actually do damage to ions. They're able to pluck out electrons and create ions from atoms. UVC, which is the part of the ultraviolet close to the X-rays, UVC is also able to change things on the atoms. It's not able to pluck out electrons, but it can push electrons to a high energy level, and as they drop down to the ground floor, to ground level, the difference in energy is emitted as a radiation. So, for example, I can demonstrate this nicely. We have a fluorescence tube. There's a gas in here. The gas fluoresces because there's a production, there's an electrode that produces ultraviolet C. And if we look at the spectrometer, we can see that there are specific wavelengths that are emitted as a result of the fluorescence. They're emitted by the gas as a result of the fluorescence. We have red, we have orange, green, blue, etc., etc. Fluorescence can also be produced by other materials. Here we have a little torch that produces UVC, and this little UVC is almost invisible. It's invisible actually. You can see very little on the table. But if I now illuminate the paper, you can see there's a very strong fluorescence, blue fluorescence here. And if we illuminate the bone has a very strong blue-green, closer to green fluorescence. This is an animal bone, this is a human bone, and most interestingly, the fluorescence of olive oil is particularly exciting because it's actually fluorescing the red in the orange color, and it's really, really exciting. So one way of checking that this is a clean, good quality olive oil. Now that's of course a fluorescence, and the good thing about the Earth is that it receives on the ground, we only receive the low energy or the middle to low energy rays. The ionized radiation, the UVC, is cut out by the atmosphere, and thank goodness for that, because otherwise life would never have emerged on Earth. We would never have been able to produce life or evolve. And it's actually an evolution, in evolution terms, it's a proof of evolution that all animals, all living things are sensitive in the visible part of the spectrum, not in the high anywhere else. And that is a very nice way of saying that it's only sensitive to the radiation that reaches the ground. And that's why life is emerged on Earth and not in other bodies like the Moon or Mars, where they don't have this protective atmosphere. Everyone knows, of course, that the visible light goes right through glass and water without any problem at all. Of course, depending on the color, this is a monochromatic laser light, it gets absorbed completely by the red color, and gets absorbed also completely by the blue color, but it does not get absorbed by the green color, because it allows through. And this is a quantum mechanical explanation. There's another video that you can look at it. But of course, visible light gets stopped very easily by paper. You can see here almost hardly anything goes through. The very, very thin layer of ceramic, which is used for electronic applications, almost nothing goes through. But of course, it gets stopped very easily by metal and by thick ceramic like this. There's nothing goes through. And the same thing happens with ultraviolet and infrared lights. But these lights, the visible infrared, ultraviolet, are actually the exemption. Because if you look at the other part of the electromagnetic spectrum, most of the other wavelengths go right through most materials. So starting from the low energy, radio waves go right through everything. At the moment we're in a basement, there's no windows here at all, it's a low basement, and yet the radio, you can hear the radio works very well. The radio waves go right through the walls and without any problem at all. And if we go a little bit higher energy, microwaves are a little bit of a special case. Microwaves go right through many materials, but do not go right through metal. Radio waves go right through metal, but not microwaves. So we can do a quick experiment. We have a little bit of water over here. If we put the thermometer in the water, we can see that it's about 21 degrees. And if we now put the water in the microwave and cover it with this very thick layered 1 centimeter thick ceramic, you can see that the microwaves will go right through the ceramic and heat up the water without any problem at all. Just like when we heat up some material, some food or something like that. Within 6 or 7 or 8 seconds, the temperature will go up from 21 to 29, as though the ceramic is not even there. The microwaves go right through it. The ceramic is almost invisible to the microwaves. And here it is, and what is the temperature? It's already 29 degrees Celsius from 21. Now if we go right a little bit higher than ultraviolet rays, X-rays and gamma rays go right through every material, whether it's metal, ceramic, anything like that. That's why we're able to look at behind a metallic barrier or anything like that. More than 120 years ago, Einstein proved with his special theory of relativity that the speed of light is always constant, as long as it's moving in the same material. So the speed of light in vacuum is the maximum, which is nearly 300,000 kilometers per second. This means that the light will take 1 second to go from the Earth to the Moon. It will take about 8 minutes to come from the Sun to the Earth. It will take about 4 years to go to the nearest star, which is the Proxima Centauri. It will take about 25,000 years to go to the center of our galaxy, where there's a huge black hole. And it will take about 2.5 million years to go to the nearest galaxy to ours, which is Andromeda. But the light has constant speed as long as it's moving in the same material. In water, it's well known, because we can see the refraction of light. It's well known that in water the light travels at a lower speed, and through glass at a different speed. And because of changing material going through water into air or into glass, we have this beautiful total internal reflection, and we have a video that you can see it in more detail in this series of videos. Well, 100 years ago, of course, Einstein, with his general theory of relativity, he proved that light is also attracted by gravity. And this is strange, because light is a pure energy, and yet it is attracted by gravity because of the famous equation which equates energy with mass. Energy is equal to mass times the square of the speed of light. A very beautiful and very important proof of general theory of relativity is that what we call gravitational lenses. That means when a star is hidden behind a very large star, or even a black hole, then the black hole has such a strong gravitational field that it actually bends the light of the star behind it, and we see the star being slightly in a different position. These gravitational lenses are actually one of the best proofs of the gravitational attraction of light and of the general theory of relativity. And finally, black holes themselves have such incredibly high gravitational field, because they have such high mass in a small area, that they don't allow any light to escape. Light that falls into them will never escape out of it. So these are the most important secrets of life. And if you think about it, life is not something obvious. 120 years ago, people didn't actually understand the nature of light. Only when we discovered quantum mechanics did we understand how light and the atoms and the electrons of the atoms, they all come together and they explain the phenomenon of light. And who knows how many secrets there are still to discover. Scientists all over the world, they're still studying light and its characteristics and its secrets.